Today I would like to talk about the transformation of equation. It's also rather complicated. But now, anyway, we are talking about mathematics. Last time we talk about some kind of a physical background of the Navier-Stokes equations. But anyway, now that we are consider the Navier-Stokes equations, especially the incompressible case. Maybe later I have a time, then also I want to consider the compressive case. And then my method, my approach is the same as in compressive. Not so big difference. Okay, so in compressible cases, okay. So now we consider, if you consider this U, then I assume that rho is constant. So essentially rho equal 1 from now on. Then what we have is that from this U equals 0. So it is incompressibilities. Namely, the volume is conserved. So this is incompressibilities, but of course, people also you can consider the equation, but more general case is plus incompressibilities. You can consider this. This is more general. Because the second equation is rho Vt or Ut. So now I consider only the Newton law, Newton flow. Therefore, here is Pi. And then it is unknown is a little bit one more than equations, the number of equations. Meaning is that the unknown function is U, rho, and T. But if equations this and this, only two. Therefore, it is one unknown function. I mean, no, number of unknown is greater than the equations. Therefore, for example, if you add this condition, it's just the number is the same. I mean, the number of equations is the same as the number of unknown. This is one way, but okay, so now some also consider this case. But also, if you consider the incompressible, not this condition. I'm sorry. The same reason as before. Compressible case, usually we assume that pressure P depends on some rho. For example, the constant times what the gamma alpha. This is barotropy. This is come from the number of unknown is one more compared with the equations. Therefore, anyway, compressive case also you need some kind of restriction on the P and rho. This is one kind of typical, very standard restriction for the equation. So pressure depends on mass density. So barotropic. But now from now on, I want to consider the incompressible case. So the most general case is, of course, you consider the equation of mass and plus this incompressibility. But it's very difficult for me. Therefore, but also this is very standard. Rho is assumed to be a constant, positive constant. And then naturally you get the incompressibilities from the conservation of mass. So this is the simplest case. Okay. And then many people work on this case. So again, I want to say that the rho is a positive constant and the divergence equals 0. Okay. So now I want to consider the equation u divergence u minus p pressure p I u. Okay, for simplicity is 0. You can also consider the external forces, or even you can consider some coupled system, or for example, MHD, magnetic field, or something. But for the simplicities, I consider only here 0 in omega t. And now divergence u, omega t. And then the boundary condition, u t is equal to external forces on boundary. So I consider the surface tension, and then P naught outer pressure, which currently meaning, and U another is U and initial data. This is our equation. I should explain this. Okay, omega t is maybe. So I consider the following case. So omega t is like here. On the inside there is some of the fixed gamma naught. So it is off. It's psi t like this. The psi t is fixed on here. So this is gamma. Outside is gamma, and the gamma is going to here, gamma t. And then this is fixed. Or this is omega. Or for example, the ocean problem, like this. So bottom is fixed boundary. And then the ocean part, I mean, Where is waves? This is also, for example, like where is omega? You catch me? So it's a very general situation, but anyway, one part of the boundary is a free boundary, and another part is a fixed boundary. So it's a very general situation though, in the mathematics. Okay. And we also consider the sigma here, surface tension coefficient sigma is, I consider 0 or positive. Also, both case. And then treatment, mathematical treatment is different when we consider the global in-time existence of solutions. So if we want to consider the large existence of solution for large time, then we need the different approach of sigma equals 0 case and the sigma is positive case. Maybe later it becomes clear. But today, what I will do is we are transform this equation to fixed boundary, because mathematical analysis is maybe should be done on the fixed boundary. Therefore, we have to translate equation to the fixed boundary case. So it takes also time on this equation. But anyway, then we consider this Navier-Stokes equations in omega t with these natural boundary conditions. So these first conditions it guarantee the conservation of momentum. And the second one is the fixed. It's a more physical boundary conditions. Is the flow is fixed on here. Okay. This picture, this omega is at least C2 Cm hypersurface. Sorry. Omega is divided into two parts. So d omega, boundary of omega is divided into two parts. This and then here gamma, the free boundary part. Gamma is Cm hypersurface. Compact. No, I will give the detailed definition of this Cm hypersurface. Now I just announce you that gamma is a Cm hypersurface. M is 2 sigma equals 0 and 3 sequence. I'm sorry that this is a very technical thing. Then usually in order to gamma t or omega t transform to the fixed omega, fixed domain omega. Usually we use the Lagrangian transformation, namely let B transpose of this vector is a Lagrangian the velocity field. Lagrangian coordinate. For a while, I Lagrangian coordinate Ym. I already explained that maybe the Lagrangian coordinate is really, in some physically, the starting point of the flow. And we are here. We here look at the flow at when t equals time t. The flow comes in. Therefore, but then okay, so let's use the velocity field of this flow in Lagrangian coordinate, our coordinate. But then also you can ask that u is xt, but is equal to byt. Yeah, because the flow is the same, just observation. So the x here, and then this point also comes from y. Then you observe the flow here, and then you find the velocity field here. But then also this velocity field you can represent v by t, because the y and the x is in the corresponding one-to-one. Okay. Therefore, so v by t is usually we call it the Lagrangian velocity field. Lagrangian. The u equal Eulerian. So u equal v. Right? This. Of course, this picture can be written in there is no phase transition. Just flow is moving in this way. Then x, Lagrangian coordinate x is y plus 0t dys ds. Okay. It's y here. Then flow is, I don't know, moving in this way. Then when time t, t, then y is arrive at x. And the velocity field is v by t. Then x can be written in this way. Okay, then we have to. This is written. Equation is written in x coordinate. Therefore, now today's purpose is rewrite this equation in the y coordinate. It's complicated very much, but anyway, you have to do this. But once you understand this transformation, then afterwards it's no problem. I mean, just only once you have to work on this transformation, then after that you can believe that the equation. Right. So let's, okay, so phi t, even not small phi t, but I want to write large phi t is y plus omega t and gamma. Sorry. Then we satisfy the boundary condition gamma 0 velocity 0. Yeah. So but this is assumption also. The velocity field, Lagrangian velocity field vanishes on gamma 0. Then y on gamma 0, then this is always 0, so y equals x. Right? So we are under this condition, just I say here, this gamma 0 is always gamma 0. So gamma naught is equal to this is nonsense, but feeling is this one. So gamma 0 is always go to gamma 0 under this condition. Okay, then of course we want to assume that this map is invertible, at least one-to-one corresponding. Therefore, okay, so the assumption is at least now we are consider t is capital T. Then assumption is gradient 0t vis yes soup norm, okay, soup norm of y omega, and then this is e less than delta is enough to, or less than 1 is enough, but for later use, anyway, this quantity is small. Number is derivative y, gradient y, gradient v with respect to y, sorry. Why we need this assumption is the following. Okay, so this is, I should keep. In fact, x1, xy equals iy plus consider 2 points. Then we just consider difference. And then you use the mean value theorem. Certain point. value sort of. Okay. Then what condition guarantees injectivities of this map? X1 minus this one, 0t minus t. For the analysis is physical tool for analysis is inequality. It is very elementary things. A plus b plus a minus b or b minus a. And then under this assumption, we can change this part. So let's say x minus 1 minus y2 delta 1 minus y2. It's okay. For theories, we can replace by this assumption. Therefore, the delta, if delta less than 1, delta is less than 1, then this inequality guarantee that 1 to 1, meaning is that y2, y equal y2. So the correspondence is 1 to 1. Injective. So usually the mathematical analysis, we always assume that this, because Lagrangian transformation should be 1-to-1 correspondence. So this guarantees the 1-to-1 correspondence. Okay. So now of course, therefore now we are also consider by psi inverse t. But it can be written also the another way, 1 plus, okay, but anyway, this exists. Then I don't care about the regularity, how much smooth of this map. Maybe later we understand. So far, this is more normal discussion. Right. Under the assumption, important things under the assumption, we have inverse map. Now we are change a variable. It's also complicated. So we have now we have to calculate this one. This is plus matrix of this. And now we consider the y to x, but it is also x to y. So then we have to calculate this one. But it's like x equal y plus 0t to b ys ds. Therefore, dx dy this identity plus nabla y b. And then this nabla is n by n matrix. I is of course n by n identity. Maybe to treat the physical equations, of course, usually the physical equations given by system of equations. Therefore, maybe it's better to understand some kind of vector notations or matrix notations. So, yeah, of course, if light the transformation is point-wise. Sorry, component-wise. This is di is ds, and then we have to consider the dyj, dxi, dyj. So here is delta ij, Kronecker delta plus 0t di yj. This is a ij component of this. Sorry, this is ij component of this. This is the definition. Yeah. And then ij component of this dx over dy is the Kronecker delta plus this one. So dx dy matrix representation is identity matrix plus 0t to gradient. Then gradient, and here is gradient b is usually this. I forgot the English. This way, y1, b2, sorry, b1, y2, b1, byn. Differentiation is this way. And then the component is b2, by1, bb2, by2, bb2, by. This is maybe a rule to represent the gradient v. Yeah, because the v is highlighted b1, bn transport. And then the differentiation is this way, so this way. And this is gradient b. Okay, so yeah, maybe at the beginning, maybe matrix representations are sometimes complicated. Okay, sorry. Yeah. Okay, therefore, what I say is that So now dx, sorry, so dy is again, I write I plus 0t tangent d ds. Then, of course, we assume that this part is small. So we have inverse matrix. So I plus. And then this is small, then you can write it is like, I write, I don't know why I prefer to use a V, capital V. And then I write K. K is a corresponding variable, so this one. So now from now on, I want to write dy dx is equal to identity matrix plus B0 sub K over K. And then this part is a function of K, analytic function of K, and K is just this one. Okay. Yeah, it's okay. All right. And then B0 K is matrix of some analytic. And then K is less than delta. So K, okay, so sometimes we consider this is a variable K, but anyway, definition domain is K is less than delta. So B0K is analytic function of n matrix of analytic functions with respect to K, and the K is less than delta. You catch this notation. Then dx was dy dx. So okay. Maybe better to write. Okay, this is, you understand. Meaning this dx is meaning is of course the vector. Okay, right. If we write B0K, ij component of B0K is equal to B0 ij. Okay. ij component of B0K, if I write B0 ij, then this relation is in the B dxi equal to this delta ij is B0 ij dyj. So it's equal to dyi. This is a component-wise representation of the change of differentiation. Right. Okay, good. Then by using this formula, we have to rewrite these equations. This is a rather big task, but then once you have to do this, okay. So to treat the fluid mechanics, I mean the mathematics of appearing in the fluid mechanics, you have to write the equation with respect to the Lagrangian coordinate. You have to know this. So it's a very boring part, but before going to the change of equations, I also want to state this normal n sub t. How change the normal n sub t is the unit normal gamma t. And this is given in the nt is equal to I plus E0 t. And here is the transpose, and then of course this is the unit vector. Therefore, divide this vector by the length of this vector. And then for later use, I also write this is n plus e n. This is for later use because this Visual K is small enough. Therefore, almost this is 1. Therefore, you can write in this way. So this is a perturbation terms. But then later, this is small enough. Therefore, how to solve the Navier-Stokes equation mathematically so far, therefore, at least for the strong solutions, so far we solve the linearized equations. So every nonlinear part is going to right-hand side, but then for example, these terms is going to right-hand side. But we may assume that this is small. Therefore, we can treat Navier-Stokes equation as small perturbation from the linear equation. Yeah? This is the main theme of these lectures. And then, as you know well, that maybe the Navier-Stokes equation, and maybe almost all the nonlinear equation, what is the goal so far is we show the existence of weak solutions. But the weak solution has a big problem, is no uniqueness. We cannot show that the uniqueness of the weak solution usually. So for example, then you know that we know existence of weak solution to Navier-Stokes equation. This was proved in 1930 by Monsieur Ray, Professor Ray, and then Professor Ray Hopp, German. But so far, it's $1 million problem is to show the uniqueness of the Ray-Hopp solution. Sometimes someone say that they can prove that uniqueness, but always so far it's wrong. Still open. I don't know. Quite recently, someone said this, but nobody believe it. I don't know. But on the other hand, we can prove the existence of smooth solution of this equation. Then this talk is related to the existence of smooth solution. Then goal is existence of unique existence of smooth solution for short time, or under some smallness assumption, we can prove that global in time exists. So this is goal so far. Maybe I don't know futures. So my talk is always related to, no, my talk is concerned with the existence of global in time as local in time, unique existence of solution to the Navier-Stokes equation, and global in time existence of Navier-Stokes equation, a small solution to the Navier-Stokes equation, with small solution for large time. Okay. Sorry, maybe my English is sorry. But anyway, so I am interested in only regular solutions, unique existence of local in time existence. Maybe better to write. My lecture is concerned with local time. Of solution. Right. Of small. Then we don't care about the how small, just small. Okay. So the point is that unique. Then both theorems can be proved. First, we consider the linear part. First, we consider linear theory, and the nonlinear part can be treated as a perturbation. So small perturbation. All right. So today's task is to derive the linear part of equations. Okay. And then I'm sorry, now that we are here, we are come here, and also so we are right. Okay. Okay. And then also kind of on the one. Then how to drive this is we are consider so so the some of the geometry y this in the product is 0. Yeah. It's a definition of no work. And then this is component wisely. Then we know the change of here. This so now what to say? Okay. D dy dx okay dyl therefore jlk equals 1 to dyl dxk dxk. Dyl is changed to this way. Therefore, formation order so this is NT. Maybe it's not correct. I mean, just the parallel to NT. So NT is parallel to this one. So NL. So in this sense, N. Okay, so we have I plus. Transpose. Because transpose is just we have here is the summation is this one. Summation. So with respect to L, so it's a transpose. So we have the summation. So it's like transpose vector. Okay, so this is a way to drive this formula. So now first we have to consider UI G. Also, we have to consider the deformation tensor. So this is the definition is a dvi dij plus 1 to n 0. Now, sorry. Yes. Plus 5 v0 ij. So no, jl vi yl here is j dyi v0 j is here, so il. So I write this one is deformation tensor. Main data. Sorry, I write deformation D. D is the deformation. This part I write this one. So I want to write this ij component of deformation tensor. Dij. And this one db. And then this summation. This is a change of deformation tensor. We write this also du. It's a matrix form of change of deformation tensor. Okay. And then next we have to give divergence. How change the divergence? U. Next, divergence U. This is of course the definition of J1 to N, Uj, Xj. So it's N, J, X, Uj. Sorry. Zero J A J Y A. This is one. So this is, you can write so B, and then B zero number B. Sorry, small. No, this is a standard semicolon is a standard way, or meaning is that okay, matrix A and B, the semicolon is you write trace of two, so it's A, I, J, B, J, K, and then you change this J, I. unknown. We should write this transpose. It's much better. Go J there, J there. Okay. But also we need a different representation of a change of divergence. So another formula is be able to obtain as a following observation. So okay, now we consider okay, so another way is rectify zero is a C0 infinity t, and then psi y. We consider this is inner product on omega t. It's u I dx omega t. Then this divergence phi is a C0 infinity function, so divergence come to here. So minus u over phi. Then change of variables. So let J is equal to Jacobi matrix of Jacobian. Of this meaning that determinant dx dy 1 plus J0 k, for example. Yeah. So then this can be right because the Jacobian is the transformation from x to y. So here, so dx is Jacobian, d dx dy dy, right? So you have u equal v, and then change of variables equal 1 plus v0. Okay, I okay. Then nabla y psi. And then where I should write Jacobian. Sorry, maybe Jacobian here. Omega. Change of values. Okay. Then again we use the integration by parts. So divergence. So this is matrix. So yeah, I plus b0 transpose. J is scalar. The b has a divergence of this psi omega t. Sorry, still phi. Yeah. And then finally we have to back to the omega. So t. So it's finally Jacobian inverse. Jacobian inverse divergence. I plus 0 transpose JD. Omega t. Therefore, another formula for divergence is this one, J inverse divergence I plus transpose. It's complicated, but so we have two forms. or is equal to divergence V plus divergence V plus 0. You have two forms. And then if U equals 0, of course it's equal to here is 0. Divergence free condition is written as follows. Beta to multiply J. So divergence free condition is div 0 transpose JB equal J times divergence V plus 0 is equal to 0. So this is divergence free condition. And now also the J is carried out J plus J0K. So depend. So for the above formula can be write divergence V plus V equals J0 B plus 1 plus B0 transpose JB is equal to 0. Sorry, 0 is equal to div B plus J0 div B plus so J 0. Sorry, this J multiply, not only this one, but also this one. So if we write G, small g is equal to minus J0 plus J0 and the vector G is this one. E plus B0. J is the scalar, this one. If we set this one, we write G is definition of this, and the capital also vector G is this. Sorry. Then the divergence condition becomes div B equal to G equal to div G. This is divergence condition. So point is that right hand side have two representation. G also can be written with divergence capital G. In another words, it's if G is LQ, then also it's intersection of H minus 1. Another way to represent this one. But anyway, this concrete representation form is much better than for analysis. Right? Okay. So maybe time is almost over. Therefore, this is boundary conditions next week. then finally, so very much complicated, I'm sorry, but then the time derivative dt ui. I quite sorry about I forget this here is important terms. I mean, dtu plus u dot nabla u. I'm sorry that. Sorry about this one. Yeah, it's material derivatives. I forget it. You have this. And then rho equal 1. Yeah, rho equal 1. If you remember that the equation of momentum, then rho times dtu plus this material derivative of velocity field, the time derivative of u is equal to this one. Sorry, I quite sorry about this. Then dtui plus nabla ui. What it is? It's now maybe it's better to write it this way. So ui is vi. That is y is equal to vi. Okay, maybe this way. Then no. Now maybe vi. The ui is equal to vi yt, but is equal to vi iy is equal to, so if you use it ui, then this is okay. So this is ux, sorry, xt, but this ux is can be written in y plus 0t es t. Now for this is a relation. So vi yt is equal to ui y, this one, right? Because of the x is given this. The vi yt is equal to ui xt. Therefore, d dt vi is equal to cos time derivative here ui dt. Also, you have the material derivative here is so gradient x ui, and then here is so the d. Yeah, just the change. So the you differentiate t here. So the first you differentiate to x of ui and times this one. And then so you have this one. Equal same. So dt ui dt ui plus nabla ui. So this is a good point to use the Lagrangian coordinate. So the time derivative becomes a simple. So dtv is equal to dtu plus u nabla u. Okay. Sorry, so this is dt. Okay, finally we have to write this part. This is very much complicated. Maybe time is over. Okay. we now stop because the time is almost over. So maybe next time we start how to represent this part, and also this one. So it takes two more times, I guess. So thank you very much today.